do? I mean, it's just click this line somewhere.
Okay.
Just click this one.
Hold this.
Yeah, or just pocket the whatever.
All right. Okay. Okay. Hello. Yeah, I'm John, and this is New Foundations for Probabilistic Separation Logic. This is joint work with Amal, Ahmed, and Steve Holtzen at Northeastern University. So a lot of our work is motivated by this question, which is we are trying to find out how we can modularly verify probabilistic programs. Probabilistic programs are getting larger as applications are using more and more machine learning, and we would like tools that support the modular verification of these larger and more complex programs. So in the traditional setting, there's separation logic. Separation logic has been super successful for the verification of concurrent imperative programs, and the key thing there is this separating conjunction connective, which says that a separating conjunction of P and Q holds of a heap if you can split the heap into two disjoint parts which individually satisfy the corresponding conjuncts. And we want something like this for probability that would allow us to kind of chop up a program into probabilistic components. Oh, the animation's a little messed up, sorry. So if you look in the literature, there are papers that try to apply separation logic to the verification of randomized algorithms. And in these papers, star pretty much means the normal thing that it usually means in separation logic. So when we write star, it means something about the disjoint union of heaps, more or less. And that's really good for the traditional notion of modularity that separation logic gives you. But in our setting, when we have probability, there's this new notion of resource, which is randomness. And ideally, we would like star to also allow you to reason modularly about randomness. And so one natural idea is, well, maybe star can mean something about probabilistic independence. And there are, in fact, papers like this. So there are a lot of papers where you write down star, and it means something about probabilistic independence. And in these logics, the semantics is based on distributions on stores. So if you write a proposition, what it means is a set of sort of distributions on random memories. In our work, we take a slightly different tack. So we have this new model of separation logic. And instead of using distributions on stores, we model a proposition by a set of probability spaces. So what does that look like? Well, essentially, if you take the old separation logic picture in the traditional setting, all we do is we replace all the heaps with probability spaces. So all the heaps become probability spaces. And then in the old interpretation of separating conjunction, the disjoint union that's used to split a heap becomes this new bulleting operation, which is an operation for combining probability spaces that we've come up with called the independent combination. That's just what we call it. And this actually leads to a logic with a lot of benefits. So what we've done is we've built a program logic on top of this for reasoning about Markov kernels. And if you look at, for example, the frame rule for that logic, it's completely identical to the standard frame rule. So this is in contrast to prior work. There are no additional side conditions you need about the random variables involved in order to make the frame rule work. Also, because our model is based on these probability spaces, these really super basic objects of probability theory, we can kind of import a lot of results super easily. So this makes it super easy to support continuous variables, makes it easy to validate like equational reasoning principles, and it also let us kind of make this modal approach to conditioning. So we have this modality, and if you stick it in front of propositions, it kind of just means the thing that you think it does. So for example, y star z, that means y and z are independent. If you stick our modality in front of that, then it means y and z are conditionally independent. And it happens with other connectives too, but this is just an example. We use all of this to verify what we consider a challenging weighted sampling algorithm. If you want to see all the details of this, you can check out our poster over there. And if you look at the poster and you want to see even more details, you can check out the paper in the link.